All right, as you can see, the question states, in the winter of 1994, record low temperatures were registered throughout the United States. For example, in Champaign, Illinois, a record low of negative 29 degrees Fahrenheit was registered. At this temperature, can salting icy roads with calcium chloride be effective in melting the ice? Assume I equals 3 for calcium chloride. Also note that the solubility of calcium chloride in cold water is 75.5 grams per 100 grams of water. So a couple of things are going on here. We know we're dealing with temperature. We also can see that there's an I listed for us around calcium chloride, which means that we're also dealing with a Van't Hoff factor. And all that's really stating again is that calcium chloride is going to dissolve, and as it dissolves, it's also going to dissociate from itself into 3 ions. So first thing we need to look at is, what is this question actually asking? So we can see that it is saying negative 29 degrees Fahrenheit is the temperature, and it's asking us, if we salt this water, will it actually melt the ice at this temperature so that we can de-ice the roads? So what we're really looking at is, will adding calcium chloride to water decrease the melting point enough to where it will actually melt at that temperature? So we are going to use the freezing point depression equation. So delta T of the freezing point is equal to the freezing point constant for our solvent times the molality of this solution. And because we know that it's a Van't Hoff factor equation, we're going to include I over there. So the first thing that we really should look at is, we know that the freezing point constant is given in the unit degrees Celsius times kilogram per mole. So first thing we need to do is look at our what we're judging against in degrees Celsius rather than in degrees Fahrenheit. So we can see that the temperature in Celsius, we know that the conversion factor is 5/9 times our Fahrenheit temperature, minus 32. Okay, so that's how we get from Fahrenheit to degrees Celsius. And when we actually do that subtraction and the multiplication, we wind up with negative 33.89, and that is degrees Celsius. So I can put that right there as well. So this is what we're going to judge against. We need to see if adding that calcium chloride is going to make the freezing point below negative 33 degrees Celsius. In order to do that, now we can utilize this equation right here to determine whether or not that will happen. So the first thing I want to look at is the molality. Recall that molality is moles per kilogram of solvent. So I'm going to come right down here, and we are going to start out with, okay, what is our solute? What's our solvent? And we know that calcium chloride is the solid being dissolved, so that is our solute. And our solvent is water. Okay, so our goal, here's our molality, and our goal eventually is to get into moles of our solute, okay, per kilogram of solvent. All right, so that's where we're going. And again, here we get to let our units guide us, okay? So we know that we start with 74.5 grams of calcium chloride, and we know that it's dissolved in 100 grams of water. Okay, now why did I put calcium chloride on the top and water on the bottom? Well, again, I'm letting my units guide me. So I know that my solvent is water, and I know that my solute is the solid, which is calcium chloride that we dissolve into there. So that's why I start with my solute on the top and my solvent on the bottom, because that's where I want them to end up with as well. So the first thing I'm going to do is I'm going to put those grams of water into kilograms of water. We know that there are 1,000 kilograms, or excuse me, 1,000 grams of water in 1 kilogram. And as we look, here I'll label these as well, at how our units cancel, first thing we have cancel is these grams of water. Pew, pew. Okay, so they're canceled. So we have kilograms of solvent right here, so we're good with water. Now we need to focus on getting our calcium chloride into moles of calcium chloride. So in order to go from mass to moles, we need to use the molar mass. So I'm going to come right down here. And the molar mass that I can find from the periodic table from the molar masses of calcium and chlorine, it is in fact 1 mole of calcium chloride weighs 110 or has a mass of 110.98 grams. Okay, so now again on the top I've got my moles up there, and on the bottom I already have my kilograms. Okay, so when I'm looking at this, now my more of my units cancel. Pew pew, grams of calcium chloride I cancel off, and I'm left with moles. Okay, so when I actually multiply those things together, I'm going to multiply 74.5 times 1,000 and then divide it by, in parentheses, 100 times 110.98. And just those parentheses are there to give us context about what's actually in the denominator, and it's really to help our calculators out. So when I multiply that all out, again, this is my molality. Remember, this is what I'm solving for initially. When I multiply all that out, I get 6.71 moles per kilogram, or molal. Okay, so I'm just going to leave it as molal for now. So that is my molality. Now what I need to look at is my constant, my freezing point constant for water. Okay, so I'm referring back up here again to this equation. I have solved for my molality. I know what I is, it's given in the problem, and the only thing I have left is that constant for the freezing point, which you can see on your table that is provided for the test. So now once I have all those numbers, I can see that the freezing point constant for water is actually 1.86 degrees Celsius kilograms per mole. So I am going to include all that information in the formula and substitute things in. So delta T F, so the temperature change for freezing is going to be I 3.00 times 1.86 degrees Celsius kilograms per mole. And my molality, which again, remember, it's moles of solute to kilograms of solvent, is 6.71 moles per kilogram. And now again, I get to cancel some things off. My moles cancel, pew, pew, and my kilograms cancel, pew, pew. Okay, and now I'm left with degrees Celsius right there, which is pretty good because temperature is measured in degrees Celsius. So when I actually multiply that out, my delta TF is equal to 37.44. And as we know, that's degrees Celsius. And as we know, delta T is not our final temperature. As we're looking at freezing point depression, remember our delta T causes the freezing point to go down by this much, okay? So we'll recall the freezing point of water, which is 0 degrees Celsius, okay? And we're going to apply that delta T, okay? So the actual new temperature that water will be freezing at with this solute dissolved in it is 0 minus 37.44 degrees Celsius. And that will give us a total of negative 37.44 degrees Celsius. So that's my final answer that I've solved, including the Van't Hoff factor. Okay, so now what I need to do is I need to compare this with the original temperature that they give us in the equation, which if we recall back up here, when we converted it to degrees Celsius, you can see that we have negative 33.89 degrees Celsius. That's how cold it was. And our new freezing point is negative 37.44 degrees Celsius. So we can assume then, or we can state then, that if I really is equal to 3, we're assuming that it ionizes fully, and there's no ion attraction in this, then the water should still melt at a temperature of negative 33.9 degrees Celsius because of this new freezing point based on the freezing point depression.